Good evening, everyone. Welcome to the week 4 live interaction session of the course Mechanical Operation. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. I think we can start our session for today. So, let me just share my screen. So, I hope I'm audible and I'm visible. Anyone can please confirm so that we can proceed further. Okay, thank you so much. So let's start our session for today. So I welcome you all to the week 4 and the last week live interaction session for the course Mechanical Operations. This course is provided by Professor Shabina Khanam ma'am from the Department of Chemical Engineering IIT Roorkee under the NPTEL SWAYAM program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering IIT Guwahati. I conduct live interaction session for this particular course for the July November 2026 semester. So we have crossed, we have come to an end to this mechanical operations course. So in the last 3 weeks, I hope we dealt concepts on mechanical operations more in detail, and I hope all of you who had taken this course and who have attended the live interaction session, I hope that you guys were able to benefit from the last 3 live interaction session. So just as a quick recap, if you see from week 1 to week 3, so during the week 1 we discussed about the basics of mechanical operations. Just a second. Basics of mechanical operations, and then we discussed about the measure, how do you basically define these particles in terms of its size and shape, different types of sizes of particles that you can measure, and we talked about how solid particles that we are going to handle in case of many mechanical operations or almost in the real life in the real life applications are not going to be in regular shapes, they are going to be typically in irregular shapes. So the size and the shape of the particle basically affect the processing and its properties, and hence its application in the particular field. So then we discussed about how to characterize the irregular shape particles. We discussed about the particle size distribution analysis. And then from there we discussed about the measurement of size, shape of the particles, particle size distribution analysis. And in the last live interaction session, we discussed also about the size reduction techniques. So we discussed about the different types of size reduction equipments that are available. We also discussed about the different types of laws that govern the size reduction process. So typically there are 3 laws that govern the size reduction. So the first one is the Kick's law, then the second one is the Rittinger's law, and the third one is the Bond's law. I hope all of you remember, since this was discussed in the last live interaction session or in the week 3 of this mechanical operations course. So then we discussed about the screening of these particles, different types of screeners, and how based on the size of the particles the screening techniques varies. So if you remember, just a second, one oh, so sorry, there was a network issue. Let me just share my screen. Yes. So I was basically giving a recap of what we discussed. So I think my call got disconnected when I was talking about the screening equipments. So in case of the screening equipments, as I said, the particles are screened using various types of equipments based on their sizes. So once you have a particle of bigger size, use uh, you often tend to use just a second. You often tend to use sieve analysis equipment, whereas when we actually move to particles of smaller sizes, then we go for higher sophisticated techniques like X-ray fluorescence and other different kind of other kind of sophisticated advanced techniques. This was discussed till week 3. Now coming to week 4, our main focus will be on particle dynamics and classification and jigging. So till now we basically discussed about the particles that are present in the solid form. They are just present as as irregular shaped particles, so they are not affected by any kind of forces. Whereas in case of particle dynamics, here we basically deal how the solids behave in a fluid medium. So basically we are going to discuss about the behavior of the solid particles in, or you can say behavior of the solid particle under the flow of certain, or under the flow of liquid. So that particular study about how the velocity of the particles is going to change with the force of the fluid is what is called as particle dynamics. So in case of this particle dynamics, we will be dealing with the certain concepts. Basically, to be specific, this will be a more mathematical session wherein we will be discussing about different kinds of formulas related to terminal velocity, hindered, settling velocity of the particles. So before that, we need to understand why particle dynamics is going to be important. Just like how do you use different kinds of separation techniques like sieve analysis or X-ray fluorescence or electron microscopy in order to separate particles of various size and shapes. Using particle dynamics also, you can separate the particles of various shapes and sizes. And so if you ask how, then typically we have to go for some of the basic techniques that we learned earlier in the secondary level, or during our school days. So we talked about sedimentation, decantation techniques, where we talk about how the particle size or how the particles settle in a fluid. So suppose if the particle is going to be, suppose if you're going to have a mixture of particles with the different kinds of sizes, the particles with the bigger, and so let's take this example wherein you have a mixture of particles and then you are going to suspend them in a liquid medium or in a fluid. The particles that are going to be heavy will actually settle down, whereas the fine particles will actually remain suspended in the liquid. So using this particle dynamics, you can also do separation of the particles. So particle dynamics becomes important concept when we discuss about the separation of the particles, and it's especially used in kind of techniques like sedimentation, decantation, filtration, and etc. Now coming to the concept part of particle dynamics. So depending upon the way the particles are suspended in a liquid, you can classify them into two different types. The flow of the fluid can actually be classified into two different types. One is laminar flow and another one is turbulent flow. So I hope anyone here who has any idea on what is the difference between laminar and a turbulent flow. This is something that we even discussed during fluid mechanics course. So what's exactly the difference between a laminar flow and a turbulent flow? Anyone? I mean, what is the difference between laminar flow and turbulent flow? It is something that is related to the way the fluid actually flows. So in case of the laminar flow, the particles that you are going, or in case of the laminar flow, the particles do not cross each other, and then they usually have a smooth motion. So you can say that laminar flow is characterized by the way in which the particles actually flow. I mean, that is what is particle dynamics. So laminar flow, as such, if you want to explain, you can say that the particles basically follow the streamlined path. Whereas in case of the turbulent flow, what is going to happen is these particles are going to actually cross each other, and then their streamlines are also going to cross. So that kind of flow where the particles cross each other is called as a turbulent flow. Whereas when there is a smooth flow of the fluid, that particular flow is called as the laminar flow. So based on the way the particles are moving, you can actually characterize the flow into two different types. One is laminar flow and another one is turbulent flow. So basically, in order to separate this laminar flow from turbulent flow, we usually use a dimensionless number called as the Reynolds number. So if the Reynolds number is up to a certain threshold, you call that region as laminar, or you call that the fluid is in the laminar flow region. If the Reynolds number exceeds the particular critical exceeds its critical value, then you call the fluid flow as turbulent. So anyone who knows what is exactly Reynolds number? It's a dimensionless number. So what is Reynolds number? How do you define Reynolds number? How do you define Reynolds number? Anyone? Let me take one more slide here. So the difference, I mean, a flow is characterized as a laminar flow or a turbulent flow based on the value of the Reynolds number. Reynolds number, which is nothing but RE. You can typically represent it in the form of, as an abbreviation, you can use the word RE. So Reynolds number is defined as a ratio of the inertial force to the viscous force. It is the ratio of the inertial force to the viscous force, and it is usually represented mathematically as RE equals to rho V D by mu. So here V is nothing but the velocity of the fluid, and your D is nothing but it is the diameter of the particle. Your rho is going to be the density of the fluid. So please be careful, it's not density of the particle, it's going to be the density of the fluid, and your mu is going to be the viscosity of the fluid. Just a second. Oh, mu is the viscosity of the fluid. So RE is going to be a dimensionless number. It does not have any units. That's what it means. So if the value of Re or the Reynolds number is less than a critical value, then you can say that the flow is a laminar flow. If it is more than that particular critical value, then the flow is going to be a turbulent flow. That means, well, when I mean turbulent flow, you're basically going, the motion is going to be very, you can say very rapid, very chaotic. The flow is not going to be smooth. So the particles are going to cross each other, their streamlines are going to cross each other, unlike in case of the laminar flow. So this is about Reynolds number. So based on this Reynolds number, you can characterize whether a flow is a laminar flow or a turbulent flow. Again, this value of the Reynolds number and its characterize and how it is going to characterize whether the flow, whether a particular flow is a laminar flow or turbulent flow, is actually going to vary depending upon where the fluid is actually flowing. In case if the flow, in case if it is about the flow of a fluid inside a cylinder, then these values are going to be different. If it is in case of a flow of a fluid over a parallel plate, then these values are going to be different. So depending upon the geometry of the surface, the flow of a fluid, or you can say the characteristics of the flow of the fluid, is going to vary, which will, and its effect, you can put it this way. So based on the geometry of the surface over which the fluid is actually going to flow, the value of the Reynolds number is actually going to change, and its characterization of whether a flow is going to be laminar or turbulent is also going to change. So if you are interested, you can go through any fluid mechanics course or book or any kind of lecture notes, so you can easily see the flow. You can easily see how different is the flow of a fluid over a flat plate and the flow of, I mean, what are the different kinds of, you can say how the geometry of the surface affects the flow of fluid. So that's what basically I wanted to say. So based on this, we are now actually, since we are talking about mechanical operations and how we are actually going to do particle separation using this particle separation in a liquid, we need to talk about the concept of terminal settling velocity. Just a second. I think there is some internet connectivity issues. I think network is very bad. Sorry, really. Let me just share my screen once again. So from here, we come to the concept of terminal settling velocity. So again, as I said, the Reynolds number is used to characterize whether a flow is going to be laminar or turbulent. Depending upon the geometry of the surface where the fluid is actually going to flow, the value of the Reynolds number is going to be different. So in case if you want to deal or learn about this more in detail, you are welcome to follow any kind of a fluid mechanics book or any kind of course that is available online. So if you go there and then you see, you can actually identify the difference between the flow of a fluid over a flat plate and the flow of a fluid over a, or flow of a fluid in a pipe. So now, since we are talking about the particle dynamics and particle separation, we need to talk about an important concept so called as terminal settling velocity. So this terminal settling velocity is nothing but it's basically about with what velocity your particle is going to actually settle down in a liquid. So here, before we basically, so in case of a single particle, we are going to talk about terminal settling velocity. However, when there is going to be a mixture of particles, then this term will, then we will talk about other kind of phenomenon or other kind of then it will be, then those systems will be characterized by something so called as hindered settling velocity. So when we are going to now, so first let us talk about single particles, then we will actually move on towards multiple particles. So in case of the terminal settling velocity, for deriving this equations, we basically go for certain assumptions, the initial assumptions with which or based on which we come up with the equation for the terminal velocity. So there are certain assumptions. Just in case if any of you know any assumptions, please let me know, or you can turn on your mic and speak up at least to any one of the assumptions. There are approximately 5 to 6 assumptions that we need to take while deriving the terminal velocity equations. If you know at least one, then you are welcome to let me know. So there are totally 6 assumptions. So let me just write that assumptions here. First assumption is the particle that we are dealing, the single particles that we are actually going to deal with are spherical in shape. Second is the particles are going to be non-porous, which means they are not actually going to absorb the liquid in which they are actually going to be suspended, and are incompressible. Then third assumption is the density of the fluid, or the density of the fluid in which we are suspending them, and the viscosity are constant. Then the particle is freely settling under gravity. Then the next one is effect of surface characteristics on the dynamics of the particle is negligible. And the fluid forms, the last assumption is, and the fluid forms infinite medium. So these are the 6 assumptions. So it is better to remember all the 6 assumptions, because we need to know under what conditions are, or under what assumptions are we deriving the particular equations. So based on these 6 assumptions, we derive the terminal settling velocity of a single particle. So first let us see, with all the 6 assumptions remaining valid, first let us see the equations for the terminal velocity of the particle. Then we will add one by one the effect of different particle, the effect of diff, once we complete that, we will basically start adding how each and every condition that we have given here as an assumption is going to affect the terminal velocity of a particle. So let's move on to this slide. So if you see here, so let's just focus on the left hand side of the of this particular slide. So if you see here, it is basically for spherical particles. This particular equations that you can see are actually derived by keeping all the 6 assumptions. So if you see the first equation, that is what is the equation, the real terminal velocity equation. 4 by 3 rho p, that is your density of particle, minus rho f, that is your density of fluid, times gdp by fd whole power half. So this is the actual velocity, terminal velocity equation of a particle in a fluid. Now fd here is nothing but it's called as a drag coefficient. So this drag coefficient is going to actually vary based on the value of the Reynolds number. So if the flow is laminar, or if the Reynolds number is going to be less than 0.1, then fd is going to be equal to 24 by re. Once you substitute that, the terminal velocity equation reduces to the equation number 2, that is gdp square times rho p minus rho f by 18 mu. So similarly, by applying different values of fd for different values of Reynolds number, we can modify the equation for the terminal velocity. So I'll just, since here I have just only represented these equations, I'll give out the conditions as well. Assumption. So if the value of Reynolds number, if Re Reynolds number is going to be between, just a second, is between 10 to the power minus 4 to 0.1, then fd, that is your drag coefficient, will be 24 by re. So once you substitute this value in this particular equation, I'll just copy this. Once you substitute this value of FD in equation, the first equation, then you will get VT as, then you will get this equation number 2. Uh, so this is equation, this is equation 1. So similarly, just a second, I'll just complete this in. So you will get equation 2. So when the value of FD is going to be 24 by RE, then the equation 1 gets modified to, is modified to equation 2. Now similarly, if the value of RE, this is the next one, if Reynolds number is between zero point 0.1 to 500 to 10,000, then you can write FD, that is your drag coefficient value, as 24 by Reynolds number, the entire value plus 0.44. So this 0.44 is based, this extra factor gets added due to the non-viscous effect. So this equation is called as Stokes law. The equation 2 is what is known as Stokes law. Now if the same value of the Reynolds number is going to be between 500 to 10,000 to 10 power 5, then FD is going to be a constant value 0.22. Then equation 1 is modified to equation 3, and this is called Newton's law. Similarly, if the value of the Reynolds number is going to be more than 10 power 5, if Reynolds number is going to be greater than 10 power 5, then FD is going to be 0.05, then equation 1 is modified to equation 4. This is equation 3 and this is equation 4. So this is how the terminal velocity will vary depending upon depending upon the Reynolds number. If the value is going to be between, again you need to actually remember this. So the better way is to remember the conditions and then substitute their respective condition to the equation 1 and then solve, or you can also remember both all the equations, that is all the terminal velocity equations, equation 2, 3 and 4, but along with that you also need to remember the conditions in which this equation is going to be valid. So the best option, as far as as far as I'm concerned, my personal opinion is that to remember equation 1 and to remember all the conditions. Based on the condition, you substitute the value of fd and then do the mathematics and then deduce the respective equation from equation 1. So that would be it would lower the burden to memorize many equations. So that is my personal opinion. It's up to you, it's your choice. So the resistance force per unit area of the particle under terminal settling velocity is given as this is the resistance per unit area of the particle under terminal settling velocity is given as Rho dash equal to the two d cube times rho s minus rho times g by 3 times mu square. And this is how you represent the resistance per unit area of the particle under the terminal settling velocity. So this is all about in case if the particle size is going to remain constant, or you can say this is all the case when the particle is spherical in nature. Suppose if the particle is not going to be spherical in nature, or it's going to be a non-spherical particle, then it will have an effect over the terminal settling velocity of the particle, and its equation will get modified. So this is the equation in case if it's for non-spherical particle. So Vt is nothing but it is in the region of Fd is equal to 24 by Re, or you can say if the Reynolds number is going to be between 10 power minus 4 to uh, 10 power minus 4 to 0.1. Then for non-spherical particles, the terminal velocity equation will have an extra factor k1, which is nothing but 0.843 log phi s by 0.065. And here the d of the particle will not be dp, it's going to be dv. That is the diameter of the sphere equivalent to the volume of the particle. This is something that we learned in live interaction session 1 or week 1 about the different kinds of diameters. So dv will be used here. And then you will have an extra k1 factor, which is represented as 0.0843 by psi s by 0.065. So depending upon the value of psi s, which you can see here, you can, depending upon the value of psi s and Reynolds number, you can actually calculate the value of Bragg's coefficient through the graph as well. Now, in case if the Reynolds number is going to be more, that is, it is going to be between 10 power 4 to 10 power 5, then you will use the Newton's law. So here also you will have a factor of C2, and dP will be replaced by dV, and C2 is represented as C2 equal to 5.31 minus 4.88 phi s. This is in case of non-spherical particles. Now, if the wall has an effect over the particle flow, then again you will have the equation will be different. So to the terminal velocity equation, you need to actually multiply with that with a CF factor, where CF is defined as 1 minus dP by d, where d is the diameter of the tube to the whole power 2.25. Just in case for irregular particles, you need to this is for laminar flow. For turbulent, the value is going to be Cf is equal to 1 minus dP by d whole power 1.5. If the particle is going to be irregular particle, then dP will be replaced with dV, and this correction factor or the value of Cf needs to be multiplied to the terminal velocity to obtain the final settling velocity of the particle if it is non-spherical in nature, and if the walls of the effect are accounted, or you can say are considered in the equation. So this is about the terminal settling velocity concept. In case if you have any doubts, please let me know. There are three conditions. So first we assume that all the assumptions are valid, and then we derive the terminal settling velocity for a spherical particles under different flow conditions. Depending upon the flow, the value of Reynolds number is going to be different, and that will have an effect over the value of the Bragg coefficient, and based on that, the terminal settling velocity equation will get modified. And we did see under what values of Reynolds number which equation will remain valid. Now we basically account for, or we basically, you can say, relax one of the assumptions, and then we consider it for non-spherical particles. In that case, same way, we need to account for the flow of the fluid based on the value of the Reynolds number. The equation will vary. So for non-spherical particles under laminar flow, or if the value of the Reynolds number is going to be between 10 power minus 4 to 0.1, then terminal velocity will have a extra factor called K1, where K1 is related as 0.843 log psi s by 0.065. And to determine the value of psi s, you basically use the plot. Based on the value of Reynolds number and the value of psi s, you can calculate the drag coefficient. Similarly, if the Reynolds number value is going to be more, then you actually go for a Newton's law. Over there, the drag coefficient C2 value varies as 5 point, or C2 value is given as 5.31 minus 4.88 seconds. Now, we also bring in or relax another assumption, that is the effect of wall over the fluid flow. Then again, we basically see whether the flow is going to be laminar. In that case, the CF factor is going to be 1 minus dP by d whole power 2.5. In case of laminar flow, it is going to be 1 minus dP by d whole power 1.5. Now, if the shape of the, and this equation remains valid if it is for spherical particles. In case of non-spherical particles, we are going to replace dP by dV. Once we do this, we basically multiply this factor to the terminal settling velocity to obtain the settling velocity of the particle and under the influence of a wall or under the wall effect. Any questions? Anyone? Now we come for multiple particles, which is called as the hindered settling velocity. So the word hindered actually means that there is going to be some interruption or interference in the settling of the particles. So hindered settling velocity is nothing but, it's basically, you can say, you can describe it in the form of a situation like this. So you're going to have a mixture of particles, and each particle is going to interfere the flow of the other particle in the fluid. The surrounding particles is going to interfere the flow of a particle in the fluid, and this is called as hindered settling condition, and then the velocity of the particles is going to be called as hindered settling velocity. And under these conditions, the Stokes law and the Newton's law is not going to remain valid. They are going to, so it's going to be very difficult to accurately predict the settling velocity of the particles. So based on that, we have some equations. So we will not see that in the form of an equation, like in the form of a concept. We have some problems. So when we solve that problem, we will be discussing about more in detail about the hindered settling velocity. In case if you have any doubts, please let me know. Or else our concept review discussion ends here. Next, we will actually move on towards problem solving session. Before we progress to that, let us take a 5 minutes break. So if you have any doubts, you are welcome to let me know. I will be here. Or if you want to take a break, you are welcome to do so. For those who don't have any doubts, and if you are staying in the session, then please start solving the problems for today's live interaction session. I will display them. So I think we can start our session. So I think the screen is still presenting. So any answers, anyone, for question number 1, 2, and 3? For Stokes' law, so let me read out the question. First question: for Stokes' law, the slope of FD versus RE. So what is the answer? Yes, anyone? So I'll just write this. FD is nothing but it's equal to 24 by RE. So now based on this, what will be the slope of FD versus RE? FD versus your Reynolds number. So it's going to be minus 1, right? Because FD equals 24 by RE. RE is going to have an exponent of minus 1. So this value will be, the slope of FD versus RE is going to be minus 1. Any questions? Okay, let's move on to the second question. Which of the following assumption is valid to find the terminal settling velocity of the particle? I think this we discussed right now. So question 2. The assumptions that is valid to find the terminal settling velocity of the particle. So option is particle is non-porous and incompressible. Option B is particle should have a smooth surface. Option C is density and the viscosity of the fluid should be constant. And D, none of the above. Answers? I think this should be easy because we just now discussed what are the assumptions for finding the terminal settling velocity of the particle. Yes, anyone? So it's going to be two options are going to be correct. One is option A, and another one is going to be option C. Because we told that the option B is wrong because we told that the effect of surface on the fluid flow is going to be negligible. So the exact statement goes as effect of surface characteristics on the dynamics of the particle is negligible. So we are not basically the assumption does not the assumption is we won't bother about how the surface of the about the surface characteristics. So whether that particle is going to have a smooth surface or a rough surface is not going to affect its settling velocity. So that is one of the assumptions that we have taken. So the question here is which of the assumption is valid. So in that case, option A and C are valid. They are true. They need to be those are the two assumptions that we consider while finding out the velocity or the terminal settling velocity of the particle. But the condition that particle should have a smooth surface velocity, that assumption remains invalid while finding out the terminal settling velocity of the particles. So next, so I hope no doubts because this is a direct question. It's just that there were two options. So if you have any queries, then you can let me know, or otherwise we can move forward for the next one. Okay. So question 3 is about hindering settling velocity or hindered settling velocity. So the question is when volume fraction of the solid increases in the cylinder, its hindered settling velocity increases, decreases, remains constant, and none of the above. So here for that you need to know the hindered settling velocity concept. So as I said, over there you actually consider the forces of the surrounding particle. So the motion of a particle under consideration is going to be hindered. There is going to be a resistance to the motion because of the surrounding particles. And in those cases, the Newton's law and then the Stokes law is going to remain, is not going to accurately predict the terminal velocity. So you need to consider there the volume fraction of the solid. So based on that, now you need to answer that when you increase the volume fraction of the solid in the cylinder, whether its hindering settling velocity or hindered settling velocity is going to increase, decrease, or remain constant. So any guesses, any answers, anyone? Take a moment of time to think about it. So any answers? Anyone? First of all, what is the formula for hindering velocity? How do you relate terminal velocity and hindering velocity? So I'll write it here. VH is nothing but VT, sorry, FS. So Fs is the factor So this is the value of Fs. And if you multiply this Fs factor times Vt, you will get Vh, that is the hindered settling velocity. Epsilon is the volume fraction of the solid inside the cylinder. So now based on this, tell me whether if you are going to increase the volume fraction, the value of Vt is going to decrease or increase. Sorry, this should be 1.8. So what's the answer? It is going to decrease, right? Option B. Because epsilon factor, because the Fs factor is going to decrease with the increase of epsilon, so the total hindering velocity Vh is going to decrease as the epsilon is going to increase. So any questions? Anyone? Okay. So let's go to question 7. Let's go to the problem solving before we enter there. So question 7 is a 0.1 mm diameter spherical particle of density 2800 kg per meter cube is free falling in a liquid of viscosity 5 centipoise and density is 1000 kg per meter cube. That is the density of the fluid. Calculate the terminal settling velocity, Reynolds number, settling velocity of the particle if it is falling in a capillary of 1 centimeter dia, hindered settling velocity of the particles if the volume fraction of the solid is 0.2. So you have 4 subdivisions to solve. The details are given. So you have a 0.1 mm dia spherical particles. It is going to have that spherical particles has a density of 2800 kg per meter cube. Viscosity of the fluid is 5 centipoise and density of the fluid is going to be 1000 kg per meter cube. Now, based on this, you are supposed to calculate the terminal settling velocity of the particle, Reynolds number, hindered settling velocity, and the settling velocity if it is falling in a capillary of 1 centimeter. I think the question is direct. So it's just that first you need to find the Reynolds number. Based on the value of the Reynolds number, you need to use the value of Fd to calculate the terminal settling velocity of the particle. So, how do you go about solving this problem? First, calculate the Reynolds number. Oh, so let me present my screen once again. So this was the question that I asked you to solve. So kindly start, please solve. So we will start solving the problem after a few minutes. So just give it a try once. So let me give out the equations. I think that would be better to start solving. If you have answers for any of the subdivisions, then please let me know. So RE is rho VD by mu, rho times V by by, oh, sorry, by mu. So rho value is given 1000. V, just a second, 1 minute. Okay, since so here the thing is velocity is not given. So first you need to calculate the terminal velocity of the particle assuming Stokes law is valid. Once you calculate the terminal velocity of the particle, you need to actually find the Reynolds number. If that value of the Reynolds number is going to remain valid for the Stokes law regime, then we can say that that terminal velocity that we have obtained is correct. So here first let's calculate the terminal velocity. Vt is going to be g. I'm going to take that as 9.8 times dp square, so that is 0.1 incident, so we will convert that into meter whole square times rho p minus rho f, so that is 1800, divided by 18 times mu. Mu is viscosity, that is 5 centipoise, so that you need to convert that into Pascal second, so it would be 5 times 0.001. So just a second. So this will be your Vt. So can you let me know what is the value of terminal velocity? I have given the expression and then the values are substituted. You just need to calculate and let me know what is the value of. What's the value of the terminal velocity? So let me calculate. So Vt is going to be 1.96 times 10 to the power minus 3. So that's going to be 0.0001996. So this value is less than zero point 0.1. Sorry, this is the terminal velocity. Now, keeping this value, we need to calculate the Reynolds number and check whether the Reynolds number value is going to be less than zero point 0.1 or not, because we have assumed Stokes law to be valid to calculate the terminal settling velocity of the particle. So again, I will just copy this. So Reynolds number is equal to rho, that is density, 1000, times velocity is 1.96 times 10 to the power minus 3 times diameter is of the particle is 0.1 mm. The whole divided by 18 times. Wait, 1 minute. Okay. Divided by mu. Mu is 5 centipoise or 0.005. So what would be the value? So 1.96 times 10 to the power minus 4 by 5 times 10 to the power minus 3. So that would be 1.96 divided by 5.392 times 0.1. So that is going to be 0.0392, which is less than 0.1. Hence, our assumption, our initial assumption that Stokes law our initial assumption is valid. Now, based on this, we are supposed to calculate the settling velocity of the particle and the hindered settling velocity of the particle if the volume fraction is 0.2. Now, how to calculate the settling velocity of the particle if it is falling in a capillary of diameter 1 centimeter? This is a laminar flow. So, how to calculate the settling velocity of the particle in a capillary of 1 centimeter? So in that case, you need to use this, you need to introduce an additional factor. So that is Cp equals to 1 minus dp by d whole power 2.5. Because it's a laminar flow, so we have to consider the exponent with the value of 2.5. 1 minus dp, that is the diameter of the particle, which is 0.1 mm, divided by diameter of the column, which is given here as 1 centimeter. So Cp now the settling velocity is nothing but Vt times this Cp. So 0.975 times point, you need to write the units, meter per second. So the value is 1.9113 times 10 power minus 4 meter per second. So this is the settling velocity of the particle. Now we need to calculate the hindered settling velocity if the volume fraction in that cylinder is going to be 0.2. So now you need to multiply the equation with that factor Fs. So what will be the settling velocity? I mean, hindered settling velocity of the particle. Epsilon value is given as 0.2. So that can be written as Fs is equal to so as per this the value will be, I'm going to substitute here, zero point 0.2 square times 0.2. So the value will be 28.7575. 0.00139. So now we need to calculate VH is nothing but VT times Fs. So we Fs we know 0.00139 times VT is 0.000196. So then the value will be 2.74 into 10 to the power minus 7 meter per second. Is this correct? Anyone with any other answers? Any calculation error anywhere? Epsilon is not so here it should be 0.8. Epsilon is 1 minus 0.2, right? So the void fraction, as per this, if you do calculation, then it would be 0.301. So it's going to be 0.0000 5698 meter per second. So this is the value of the hindered settling velocity of the particle. So any doubts in this, any kind of errors? I think there's a mistake here. This should be. Now it is perfect. Any questions so far? Anyone? Or else we can move to these three. So we have one problem, and I think this problem is similar to what is here, just the values are different. So I think you can solve this. So let's move on to these three questions quickly, and then before we wind up our session. So let's move to question number 6. When the fluid flows in a streamline, that flow is turbulent, laminar, transition, or none of the above. Transition is basically a flow condition wherein it moves from the laminar region to the turbulent region. So which is correct? When the fluid moves in a streamline, the flow is laminar, right? So yes, the correct answer is laminar. Now come to question 5. Materials A and B, where rho A is greater than rho B, are to be separated through jigging. So large size of particle A. So what will happen in that condition? Large size of particle A will settle down before small size of particle B. Small size of particle A will settle down before large size of particle B. Both A and B, and none of the other. It's going to be both A and B, right? Because both, in case of this jigging condition, there are chances of both. For large size of particle A to settle down before small size of particle B, and small size of particle A to settle down before large size of particle B. So both are correct. Now come to question 4. In a cylinder of given diameter, settling velocity decreases as particle diameter increases, decreases, remains constant, and none of the above. Remember, the expression is 2.5. So if the particle size, if the settling velocity is going to decrease, that means Cp value is going to decrease. So under what condition of particle diameter Cp value will decrease? dp should increase, right? So if dp increases, dp by d will increase, 1 minus dp by d will decrease, so cp will decrease, so that will cause a decrease in the settling velocity. So dp by d should increase. Now, so any questions, anyone? I think this is our last live interaction session. So in case if you have any questions. So in case if you have any questions, you are welcome to let me know, or else we can conclude our session for today. Anyone? Okay, so thank you all for joining today's live interaction session. I hope this session was useful. So our next live interact. I'm sorry. So this is our last live interaction session. So I hope all these 4 sessions were useful to you. So mechanical operation is something that goes even beyond these 4 weeks. So if you're really interested in mechanical operations or particle technology or powder technology, you are you can always explore. So there are lots of reference textbook and courses that are available online. So you can always delve deep into the subject to learn more about it. So I hope all these 4 sessions was useful. This recordings will be made available to you. I hope you are able to access the recording through the course content page. So let me tell you again. So if you go to this mechanical operation course NPTEL page for the July-November 2026 semester, on the left hand side you can see the problem solving session. If you click on that link, you will be directed to an Excel sheet. From there, you can actually access the YouTube recordings of these videos as well as the NPTEL presentations. So my email ID will be available along with the presentation. So you're welcome to email me. I will respond to your queries as soon as I can. So I take this as an opportunity to thank Professor Shabina Khanam ma'am as well as the NPTEL team for providing me this opportunity to interact with you all. So thank you and all the best for your future endeavors and bye.